And we're off again.
Today's agenda is to continue on with that. Complex number, we've looked into something called complex square roots, and it ties in very nicely with the first heading, which is a bit more general, where it's not z squared, but z raised to any arbitrary exponent. The first thing we're going to look at is how do you solve a division. We will see how to solve it both algebraically and geometrically, so you can understand what is happening in a diagram. Now let's explore the relationship between the old-fashioned numeral signs we use in real numbers and modulus, which we can use to describe circles on a plane with complex numbers. Finally, we'll take a look at the complex exponential function. Time permitting, I'll also discuss the complex logarithmic function a bit. We'll see how we get on. But let's begin with the main topic, which is the binomial equation. So for those of you taking notes, the heading is the binomial equation. And this is basically an equation where you pose this particular question. Is there a number set that's complex? So if I multiply it by itself once, it becomes another complex number w. So as you can see, this equation looks a lot like the one we've solved together a few times, called z squared equals w, where we were looking for the square roots of w. But now it doesn't say z squared, now it says z to an arbitrary exponent n. And n is an integer, you have to imagine. So n is integral. And what we need to find is z. So the task is to find z, and there's more than one z. For instance, if it says z to the third equals some complex number, then there are 3 solutions. If it says z to the 7th equals some complex number, then there are 7 solutions. So we need to figure out how to find those solutions to such an equation. What we know is w, and what we need to find is z. Just like you saw when I wrote about square roots, we know w.
Complex numbers will be known.
And let's say we know w in polar form, written using Euler's notation.
Our walks are in the countryside. That's what we're used to.
And let's say that phi up there, we've chosen it to be a principal argument. And we know that means if it's a principal argument, then it falls within the interval from, but not including negative pi, up to and including pi. And let's also say that the number z we're looking for, we imagine that it's easiest to find if it's also in polar form, written with Euler's notation. So the number z we're seeking is this one. If we need to find it, we're on the hunt for values, and we write z like this. R times e raised to the power of I theta, where what we are looking for is the small r and theta. And if we can find the small r and theta,
now you've got something to think about.
And if that equation is satisfied, what have we found? We've found all the solutions that result in w when raised to the nth power. So we found all the nth roots of w that exist. And we're used to it not being that hard, because if it were just like this with good old regular numbers, find me a number that when cubed equals 8. So we've learned that there's only one answer, right? And that's 2, because 2 times 2 times 2 equals 8. But if we have z cubed equals 8, then there are 3 answers. When looking for complex numbers that when cubed give 8, there are 3 solutions. And that's what we're going to look at. Let's start by taking this expression from z and putting it into the z's place. Then we get an expression that reads parentheses, r, e, I theta, all that in the end. It should equal w, but remember w was capital R, e to the power of I times phi. So the expansion that's coming up now, it looks very much like the one you've practiced for the square root. There's a slight difference, but it's not much. So if you can do the other, you're well on your way to only doing this one too. Then we use the fact that a product raised to a power is each factor to that power. So we can rewrite this as r raised to the power n times Euler's number raised to the power I, theta gang, and you're going to change that. And there we have it. I have just raised that to the nth power and raised that factor to the nth power to get this result. And on the right side, I haven't done anything. So I can just copy down what was written before.
Research, engineering, innovation, intuition, future initiative.
So here we have a power rule we can use. We need to multiply the exponents. As it's a power raised to a new exponent, there one must multiply the 2 exponents. So now we can rewrite it like this. R to the nth power times e raised to the I times
Exactly.
n theta. And on the right side, I'm copying and pasting again because I haven't changed anything there. Now let's do what we usually do. We can say that if we have two complex numbers that should be equal to each other, which we have here, because this one is a complex number and so is this one, then they must have the same modulus.
And they must have the same argument, except for a whole multiple of 2.
So that means if two complex numbers are the same, they must be equally distant from the origin. They must have a modulus, and they must be rotated to the same angle to be in the same position. But the angle they are rotated to can well be expressed with a whole or two whole faulty rotations. That's what I mean when I say except for an integer multiple of 2pi. So this equation basically generates two equations, equation 1 and equation 2. So equation 1 is that the magnitudes must match. Our magnitudes must agree. Thus, R subscript n should equal the big R. They have to, because otherwise they don't have the same modulus. So the small rn must equal the big R, and that's because everything that stands in front of Euler's number here, when written in Euler's notation, is our modulus. So little r sub n, that is the modulus of this complex number. And big R, that is the modulus of that complex number. So little r sub n must equal big R. But we can solve that one immediately because this is a good old-fashioned real equation. Why is that? Well, because little r is a positive number and big R is a positive real number. So I can solve this by simply taking the nth root on both sides. So little r is equal to the nth root. I'm standing here. We'll underline that because now it's solved completely. We found it. Modulus is corresponding. And if we interpret that right now, what does it mean? Well, imagine, for example, it said setiente, then we write it as 8. So I know right away that the modulus is that number. It's 8.
It's a year date.
It's on a circle with a radius of 8. And the cube root of 8, that's 2. So then I know that all the points lie on a circle with a radius of 8. So this is actually what we're figuring out here. Let's look at the angle. I mean, the argument n times theta. This is the argument for this complex number n times theta. It has to be equal to the argument of this complex number minus a whole number of turns. So it has to equal phi minus a whole number of full rounds. Except for an entire number of full turns, and one full turn is 2 pi. So this is the part, if you want to sound fancy at an exam, where you say, except for an integer multiple of 2 pi. That means an integer times 2 pi. So p has to be an integer, and we write that down like this. P can only be chosen from the set of integers. So that means 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Those are the integers. And this line we've already completed. This next one we haven't finished resolving yet, because it turns out there are many solutions down here. How many solutions are there then? It turns out there are exactly n solutions. And we find them by thinking, okay, what is the first whole number we could let p be? Well, it's 0. So let's try putting p equal to 0 first. So if I set p to 0, and you've partly heard this story before because that's how we did it with the roots of equations too. We started by putting p at 0, and if p equals 0, then I can find theta corresponding to p at 0. So I call that theta. And I just find it by dividing this equation by n. So phi stands alone.
And that means it's going to say fi, which needs to be divided by 1.
And when p was 0, this term disappears. So there's no more diving needed for your men. That's the answer. This here is an angle that works. At that angle, there's going to be an nth root of w. Are there any others? Yes, there are. Let's try putting one in. If I set p equal to 1, what do we get? Then we have n raised to the power of 1. N raised to 1 equals 5 plus 1 times 2 pi because p is now 1. And that means when you divide the equation by n, it says phi equals 1 over n. Plus 2p. I will certainly do that. So there's also an angle there that works, which is theta 1. So we can underline that one as well. And then you can just continue down the line with PD0, PD1, PD2, PD3, PD4, and just keep going. And it turns out that the last value that works is n minus 1. So eventually you get to n minus 1. For instance, if it says set at 8, how many different solutions are there? Exactly 8, it turns out. And the first one starts with 0. So the last one ends with 8 minus 1, which is 7. So you get 0, 1, 2, 3, 4, 5, 6, 7 as different values for p. So I can imagine that I'm now experiencing something down there for p equals n minus 1. What does it say then if I set p to be n minus 1 up here in this line? Well, it says n times theta. Theta n minus 1 equals phi plus p gang 2b. But if p is now n minus 1, then I can replace the p with n minus 1 right there. That's what I'll do. So that's what I'm doing. And then I can isolate theta n minus 1. Now I just want to divide the equation by n, so I get phi over n plus n minus 1 times 2 b over n. And this is the last angle that works, this one. And why is it the last one that works? That's because if you try to set p equal to n, then that would be the next value. Look, p equal to 1, 2, 3, 4, 5, all the way to n minus 1. Then you take the next one that comes after n minus 1, which has to be n, right? But if we set p equal to n, let's just try that over here. Then we'll see what we get if we set p equal to n. Then you'll see I end up with something I've had before. And if I set p equal to n, then it will end up as n times theta n. The product of theta and n. Are you in with phi? P times 2pi, but p and un. I'm going to p. If I now divide through by n, what does it say then? So it states that Ctn, it will be fine indeed. And then add 2.
Professional interest group.
Divide by n to isolate theta. Now you can see the n cancels out with n. And here I've added a solution that I already knew beforehand. Because the end date, what was it? It was the very first one. That was the one I had indeed. So it would be repeating a piece of advice I've already found. A final piece of advice that was already determined. And this means that what I've demonstrated now is that when solving the binomial complex equation of the end point, there are precisely n different solutions. And as you'll see when I work through an example for you, they all lie on the same circle with a radius that's the nth root of r, where the big R is the modulus of this w. And they all lie at the angular points of an equilateral polygon. And you'll see what I mean when I calculate an example for you. But now we have the solution. The solution looks like this. What do all the nth roots of w look like? Well, they look like this. You find the nth roots of w by taking the nth root of r, which was the modulus of w. And then you multiply it by Euler's number, raised to the power of I, times I, and then the angle here, it's right here. Or if we're going to write it in a more general way, so I just had to isolate theta in this one, so it yields the third part, plus p group times 2pi end to end. This is the formula, and this is how you do it, as we've just shown. So I just need to jot down which p's work, and they are these ones right here. And then you stop at n minus 1, and then you're done. So here's the conclusion. This is how you find the n. Different tips provide conflicting advice. And before I demonstrate an example, maybe we should see if anyone has questions. Usually it's easier to grasp what I'm doing here once you've seen an example. So I started with the abstract part, and then I'll show the example. Sometimes I do it the other way around, but today I might be doing it a bit unconventionally. I begin with the proof, and then I'll show the examples. If there was something here you didn't quite get, I think it'll make sense once I walk you through an example. But that was all right then. Does anyone have any questions? Shall we try an example then? So I can try to leave everything except for this formula right here. Or we keep everything except for this formula. Then I'll just leave it like that so we can use it. Here comes an example. Imagine we have to solve an equation for a number we don't know, z, raised to the third power, equal to the imaginary unit. So we ask ourselves, are there any complex numbers that have the property that if you multiply them by themselves 3 times, you end up at I? To understand this, let's start by sketching where I is located. So here comes a little version of the complex plane where we'll just mark where I is located. So here is the real axis and here is the imaginary axis. And here lies I. The imaginary unit is 1 unit up on the y-axis. That's the imaginary unit. So what we're looking for is whether there are any points on the complex plane that, when multiplied by themselves 3 times, end up there. That's what comes next. How far is it from here up there then? Well, the distance is 1. And that means that the modulus of that number is 1. So I can rewrite this number as 1 times Euler's number, raised to the power of I times this angle here. And what angle is that? 90 degrees. 90 degrees, that's the same as half radians. So that means the I we have up there can be rewritten in this guise as e to the power of I times pi over 2. And if you could just compare that with the proposal when we had just written it down before, then here it is. That is stood R, the number. It stood R.
And Fi, the one up there, that's half of Fi.
And then we can basically try to fit it into this formula right here. Head straight into it and find the answers. So let's give it a try. Let's find the first set that works. And the first set that works is the one where I use P to denote 0. The next one that works, that's the one where I set P to be 1. The following one that works, that's the one where I set P to be 2. And the next one, which is a repeat once I found it, is where I set P to be 3. That will just repeat the first one. So there are no others different from each other than the ones corresponding to P0, P1, P2.
There are only the 3 different cube roots of I.
So the first one I find, I call it Z0 because it corresponds to setting P equal to 0. So then it's just a matter of plugging it into the formula. What do I need to do? I have to take the nth root of W. But what is n? It's right there. It's wrong. So I need to take the cube root. So I need to take the cube root of I, but that's equivalent to taking the cube root of R first. But since R was just 1, I can simply write a 1. Now I'm over here in the formula, starting to plug in the values. So in the I blink case, raise I, the imaginary unit, times, and then let me just write down what's written here. It says take phi and divide by n, but I know phi well, it's pi over 2. So here it should say pi over 2, and that should be divided by n, but my n was 3, so it should be divided by 3. And then I should say plus p times 2 pi over n, but this comes out to 0 here, because right now I have chosen p as n. So the first integer value for p that I chose was 0. So that's why it just gives that there. And we can just finish that calculation because the cube root of 1 has to be 1 itself, since 1 times 1 times 1 is indeed 1. So this is the same as writing 1, which I can't be bothered to write, times Euler's number. So I need to calculate pi over 2 divided by 3, and that would be pi over 6, because when you divide a fraction by a number, you multiply the denominator by that number. So multiply by pi over 6, and here we have the first solution. So what exactly is this number? It's the number that has the property that if you multiply it by itself 3 times, Shakiri. And can we sketch where that number is located? Yes, we can.
We're looking up at the sign.
So let's clear away all this fuss so we can see what's going on. An angle of pi over 6. How much is that?
It's like doing a 180.
And that gives us a sixth. It must be 30 degrees. So I just need to go up to 30 degrees, and I still have to be a long way off. Imagine that you have a unit circle here, and we have moved up to an angle of pi.
Seriously, that's it?
And there we are.
Of the 1/3 root of I.
So does it make good sense to us that this is one of the answers called zero? This here, this is zero. Oh yeah, that does make sense, because just listen for a moment. When you multiply a complex number by another complex number, you have to multiply their magnitudes. And then you add up their arguments. Remember that. So if I take this number and multiply it by itself, what do I get? That angle plus the same angle again. It ends up there. When we double the angle, we reach 60 degrees. And if I multiply the number by itself once more, I end up right there. Can you see that? So this number called Z0, and otherwise expressed as P over 6, if I multiply it by itself 3 times, I end up with Z0 in third power.
EEIPHTOL gang. EEEPHTOL gang. EEEPHTOL gang.
But you can see there that you have to add the exponents together because it's a matter of multiplying powers with the same base. So this should yield the visual condition raised to the power of I.
5 divide plus 1. 5 divide plus 1. 5 divide.
And there's I as a common factor, so I can put that outside the parentheses.
Picture part plus picture part plus picture part. That's 3 picture parts. It becomes half.
So there I just give e to the pi over 2.
But you guys write in a completely different way.
So you can.
So I found a number in the tree I'm giving input to, and the code is EIIPCHD.
And what does that make this number? It makes this number the cube root of I. But that's just one of them, because there are 2 others that we also need to find, and that's coming up now. Now we take PB1 and find the next one. If I set PB to 1 and use this formula again, what do I get? Then I put 1, right? Because set 1 means the set value that belongs to the whole number value P equals. And once again, I need to take the cube root of 1. Just like before, because I'm using the same formula as before. So it's the cube root of 1. Multiply by e raised to the power of I times parentheses. So I must say 5/7, which remains pi halves divided by 3, just as before. But now pi isn't 0, now pi is 1. So it states 1 times 2 pi divided by 3.
So it's going to say plus 2p.
It's divided by 3, because 1 times 2 pi still obviously gives us 2 pi. So this is the next solution, and we can also finish writing it, because the cube root of 1 is still 1, which I can't be bothered to write, times Euler's number raised to the power of I times. So what do we have here?
Shoot.
A third plus 2/3 pi.
I'm sorry.
1/6 plus 2 pi over 3. This can be combined by extending it with 2 pi in both numerator and denominator. So it also becomes some sort of sixth. So here I actually have pi over 6 from this, when I multiply 3 by 2. And over here, I extend by 2. So I end up with 4 pi.
We're on, you called it.
And 1 PCA part plus 4 PCA parts. That makes 5 PCA parts. So this can be written as Euler's number raised to the power of I times.
That's it. 6th fire.
So this is the next third piece of advice from me. So one might ask, is this a main argument?
Yeah, it is.
Isn't this number a bit smaller than for the girls? Because if there was a 6 up there, that would be the peak. So it has to be a bit less than peak. Then a 6 would be out if there was a 6 figure. So that's solid. It's a main argument.
And where can I find this number then? Well, if there had been a 6 up here, then it would have been placed here.
But actually, that's not the case. It's exactly the pi-shaped section smaller. And we figured out earlier that the pi-shaped section is 30 degrees. So it has to be 30 degrees before that spot. So it must be right here.
So here lies Z1. It's been erased.
And then maybe we can look at the drawing and say there's sense in it. If I take that complex number and multiply it by itself 3 times, do I end up there? Yeah, take a look here. When you multiply one complex number by another, you multiply their magnitudes and add their arguments together. But the magnitude is easy because the magnitude is 1, and 1 times 1 is still 1. So if you start on the unit circle, you stay on the unit circle when you multiply a number by itself. So that means when this number multiplies itself, it results in this angle here, added to itself. Just like that. So I end up here. Can you see it? And then I
If I
multiply.
say it again, then I'll end up there.
So
It says
that
this is the number here. Multiply this number here. Multiply this number here.
I should end up right up there. Let's give it a try out here. Let's see what C1 to the 3rd power gets us. Let's calculate that.
So this is something you don't normally do. It's just something you quickly do on a piece of
For
paper.
yourself, to be sure, right? So it gives EII 5 P6 delete gain E1 1 5 P6 delete section E I 5 P6 out.
Then I guess I have to say this plus this.
With the rules of exponents. So that gives e raised to, and what do we have then? 5, 10, 15, pity 8 parts.
15, 10. Seriously? I do.
And play along with it.
So you might ask, how many times does 6 go into 15?
It does that twice, and then there are 3 left over. So if you were to write it using elementary school notation, you would write it like this, EII, and then you could write 2 pi.
Because 2 goes into the first one. So 2 arrows up.
Plus minus 10 halves.
Because 2 pi plus half of pi equals 15 pi if you bother to do the math. And then you can see that this means that this number multiplied by itself 3 times goes a full circle, and then just 90 degrees further, and it checks out. Now we just need to find the last one. So I'll set p equal to 2, and then there are no more. Because if I set p equal to 3, I'd find one I already found. That would mean I'd just be repeating the solution that was already there. So there are only 3 geometrically distinct solutions, and they all lay out neatly. Now let me just draw the last one. It's right here, C2. So it's worth noting that there are exactly 3 Z0, Z1, Z2, and then if I connect them with each other, so they sit like the vertices in what we call a polygon, an equilateral polygon at that, because all its sides are of equal length. And that's always the case. The solutions to the binomial equation sit as angle bisectors in an equilateral polygon, inscribed in a circle with a center at the origin, whose radius is the nth root of big R. How do you ever learn to say all that? Only by practice.
I've practiced. I've said it so many times.
And because it's been said so many times, it doesn't even seem hard anymore. But in the beginning, I thought this is something I'll never learn to say. But just look at the drawing. The 3 solutions are right there as the vertices. A polygon means a many-sided figure, polymany-gon side. And the sides, because they're always of equal length. And then it's inscribed within a circle. Can you see? And what is the radius of that circle? It's the nth root. I'm clueless about WI. Let's just find the last one. And once we've found that final solution corresponding to PL2, let's take a short break.
So here comes the last one. Where do I have space for it? Maybe over here?
At least there could have been blackboards, you know.
Stick into.
So again, I need to find the nth root that corresponds to 2. I'll call that Z2. And I take the emperor R, which says that I take the cube root of 1. The product of Euler's number raised to the power multiplied by phi, and this was 3. And phi, which was pi over 2, so pi over 2 divided by 3, plus, and now times 2. So now I'm putting a 2 in there, and it's going to be 4 pi.
Divides by 3.
And then we can just finish the calculation. This gives us, as usual, an e raised to the power that we don't bother writing down. And then we need to consider the P6 parts. And over here we have 8 P6 parts. So P6 parts
plus 8 P6 parts, that must make a total of 9 P6 parts. But is 9 P6 parts the main argument?
It's over 180 degrees here.
So in principle, you should actually go backwards instead of calling it minus P half. Because that's Helena, that's me. This is actually a new PCA part. Why is that? Because it's 9 times 30 degrees. Because the PCA part is 30 degrees. And 9 times 3, that's 27. With a 0 after it, that's 270 degrees. 90 plus 90 plus 90 equals 270 degrees. So we end up there. But we express this by going backward because we want it as a principal argument. So this can also be written as Euler's number e raised to the negative IP over 2. I'm just going backwards with the angle here to make sure that it's the principal argument.
Oh, that's the final solution. That one.
Yeah, that's right. If you take this number and talk to yourself 3 times, you end up with I. Yeah, check this out. Here we are. So we multiply this number by itself. Then we need to take this angle and add it to itself. And that's what we'll do. So we'll end up there after we've done it 3 times. So what we're actually discovering with complex numbers is that they represent operations in the plane, their rotations.
There are expansions and there are compressions in the design. That's what complex numbers can do.
That's what they can do for us. They can describe everything that happens in the plane.
and that's why we teach them, because a lot of things happen in the plan.
Are there any questions? All right, Millen. If you want to pause our recording, then let's take a break. So we just took a break, and before the break, we derived this formula. How do you find the nth root of a complex number? You take the nth root of the modulus of this complex number, multiplied by Euler's number, raised to the power of the different angles listed here, by letting p be one of the numbers written here. And that means, given that p can take the values 0, 1, 2, 3, up to n minus 1, there are exactly n distinct nth roots of w. Let's work through an example so you can see how it's done. Then I'll write some exercises on the board for you to try and puzzle out while I walk around and assist. All right, let's tackle another one. Let's try to solve this one. Example 2. Give me all the sets of complex numbers in the cube. It's the number 8 times Euler's number raised to the power of a.
So what does he come up with now? Right, 8 times e raised to the power of I times pi. What number is that?
It's the number that is 8 away.
At least suppose that.
There are just infinitely many
That's
of them.
all of them lying on a circle with the center at the origin and a radius of 8. But the angle is 180 degrees. So that tells me I'm out on the negative part of the real axis.
There's a salmon detail here, so they're drawing it. So I'm just going to rotate
That's
pi
how
around.
it is. You cut 8 away. It might be right here. So here lie the old-fashioned numbers, minus 8, which we all know.
So this right here is the number -8. But I'll just leave it like that. And why do I do that?
It's because if it says something like that, I can read the modulus and I can read the stats.
Argument. Is pi a main argument?
Yes, that's right, because pi is in the range from negative pi up to and including pi. So I can just plug it straight into this formula, and then I can find the 3 of them. So let's find the first root, z0. That's the one that corresponds to when I set p equal to 0. That's why I call it z0. So it's a bit illogical that the first one is called z0, but it is. It might be called z1, but it corresponds to the whole number value 0 for p. That's why it's called z0. Then I plug it into this formula, so I have to find the nth root of r. I need to find the cube root of 8. So let's start off by writing that down. Because it's right here. That's what you. And then over there, cowardice. And that right there, that is n. And then it's just about using the formulas.
Once Euler's number raised to the power of I, let's get started. And then we need a phi fraction, which means we say pi divided by 3.
Just like that. And then I'll say 0 because I'm starting with p set to 0.
and 0 times 2p over n gives me 0. So this disappears. So this must be the first solution, and I can finish calculating it, because the third fraction is 8, which is of course 2. So there you have it, first solution. So that's it, the first solution.
And where is it located? Well, it's rotated up at an angle that's 3 times less than pi.
So if this right here is p, which is 134 degrees, then I must say that 180 degrees divided by 3, that's 60 degrees. So the first solution lies, and now I decide if I should make a new drawing. I probably should.
Don't go making any new incline.
The first solution is rotated up to 60 degrees.
And how far should it be? 2 away. So I need to draw a circle with the center right here and a radius of 2.
And here lies z0. It was the first solution. So does it fit that if you multiply this one by itself 3 times, you end up with the output, -8?
Take this number here and multiply it by 3 times. So do it like this. 1, multiply 3, and it lands right here. Then take 2 and multiply it by itself 3 times, 2 times, 2 times 2. That's 8. Then move it like this, and it ends up over here at -8. So you can see it fits.
That was such a clever observation. Once again, I have to take the 3 of diamonds 8.
The Euler's number raised to the power of p 1/3, and then add, and now p1. I've now chosen the next whole number value for p. So now I will say 2p over n, that is 2 pi over 3.
And what does pi over 3 plus 2 pi over 3 give us?
Well, that's 3 pi over 3,
Also known as pi.
so this can be written as 2e to the ipi. But what number is that? It's like the number -2 in disguise, because pi is 180 degrees. And 2 away, because I'm rotating 180 degrees and I'm 2 away. So the number e is at -2. So the next solution lies here. Out at -2, that's where C1 is located.
This is actually the number -2.
Because the angle of P is 180 degrees. And when you're at a distance of 2 from the wall, rotated over by 180 degrees, you end up at -2.
Does that work for you
If you
then?
multiply it by adding 3 times,
You get the number.
it says up here that it was -8. Yes, it does. -2 times -2, that's +4. And +4 times -2, that's -8. It checks out. So you can see the one root that we are familiar with in real numbers also appears. We get that one too. So those good familiar real cube roots, they come along too. And then we get 2 more as well, because we're in the complex plane. Is that a principal argument? Yes, we can often let that stand. It's all good. Now for the last one. It's 2 again, because we need to take the cube root of 8 and multiply by Euler's number raised to the power of I times parentheses. VA divided into parts, which means PA thirds. And now I shouldn't say 2p divided by 3. I should say 4p divided by 3, because p was 2 now. Just like p.
Am I listening with Wood?
And if we just write it out, it yields 2 raised to the power of Euler's number times 5 pi over 3. It's right out here. Can you see it? So it's right here.
It's located out here off the beaten track. Can you see it? So it's right here.
And notice that there is a light wooden edge here.
It's a police sting.
And if you connect the corners, maybe you can see it better.
But if this is 60 degrees, then this must be -60 degrees, because that's not a principal argument. Since it's over p, if I want to express it as a principal argument, then I need to write 2 times raised to the power of -I.
Times, and then we need to put image 30 in there, right?
That was the last piece of advice. Did you get that? All right, I'll try to come up with 2 tasks in just a moment after I've taken a picture of the board, and then we can give them a shot. So you could start by working out the derivations in pairs at the tables, just so you get some practice. Maybe you should try solving the problems first to get a feel for it. Here come the 2 tasks we're going to try to solve now.
Hey, kid.
Yes,
What's up with?
a 16.
Can you feel that? Don't multiply by pi.
Okay, 1, 2, 3.
See you then.
L.
See you. Solutions.
Self.
It's unanimous.
It's the 4th in W. And draw the solutions.
Fine.
All right, deal. Let go. The binomial nomenclature. It's the 3rd one at least. And submit all solutions with main arguments. So you don't have anyone else to play yet. So let's just pause the camera here, Milan, and then we can try to solve those 2 tasks there. So now we've looked a bit at the binomial equation of nth degree, where we've learned to extract nth complex roots. Next, we're going to look at the relationship between numerical signs, as we know it, and modulus, and what it can be used for concerning sets of points in the plane.
So let's take a look at board 5.
So let's try to take a look at the numeric sign, because we've covered it before. And maybe we never really finished thinking it through. I know I hadn't until I got to complex numbers at least. So let's start by taking a look at that numeric sign, which we've learned about once.
What does it mean to say numerical value?
To explain this, let's just start with some really simple examples. The numerical value of 2 is equal to 2, because the number 2 is 2 units away from 0. So it can be drawn. Here's the number lane, here's 0, and here's the number 2. And when you put these 2 vertical bars around the number 2, it means how far the number is from the origin. And we can see that it's 2 units away. So therefore, the numerical value of 2 is 2. So if I ask, what is the numerical value of -2? It's also 2, because -2 is right here. And we can see that the number -2 is also 2 away, since the distance can't be negative. So the distance to the number -2 is still 2. 2 what? That's not something to worry about if it's not
It
specified.
could be 2 meters if you're a physicist, or 2 light years if you're an astrophysicist.
It gets a bit more complicated when there's a number sign with an X in it. What if it says like this? Just find all the numbers that are at a distance of 2 walls from eco. That's what it says here. It says a number you don't know lies at a distance of 2 walls from eco. How many options do we have? The 2 possibilities. Either it's 2 we're dealing with, or it's -2 we're dealing with, because both those numbers are at a distance of 2 from echo. And how could one find the 2? Well, you could draw a circle with the center at eco and set the compass to the radius.
To 2, and definitely not drive around in a circle.
And where the circle intersects the number line, that's where the solutions lie.
Can you see it?
So this here,
Exactly the circle that contains only 2 points. But when we get to complex numbers, it becomes full circles. Because now we're no longer just on a line. Now we're in the entire plane. So to solve this equation, you write down to yourself that this equation means that either the inside has to yield 2, or the inside has to yield -2. And those are the 2 solutions to the equation. Let's try working on an equation that's a bit more complicated. Still a real equation. What if it says that the numerical value of x minus 3 must not be 2? What does it say now? And we need to think deeply to truly understand this. And to really grasp it, we must understand it thoroughly. So let's try to draw it, because the drawing is always what gives us the deep understanding. Here's the number line. There's 0, and I'm not going to draw anymore because I haven't understood anymore yet. Then I look at this and ask, what does it actually mean? Can you find some stuffing as a distance of 2 brick layers away? But then there are 2 possibilities. Either the guts have to each time take 2, or the inside must each number -2. The possibilities are just as good. If I just finish solving this one first, what does that give us? Sure, to solve this equation, I just add 3 to both sides. And if I add 3 to 2, I get 5. Then I solve for one solution.
Does it work then? Yes. Take the number 5 and fit it into the excess space. Then it says 5 minus 3, that's 2. What about the 2 now? It's 2. That should be fine. It works.
Are you there?
To solve this equation to completion, you add 3 to both sides of the equal sign. And if you add 3 on top of -2, you get 1. Does that work? Plug in 1 there. 1 minus 3, that's -2. The absolute value is -2, which is 2, money fits. So there are 2 solutions. Here's one, here's the other. But we still haven't understood it. We've only done the calculations. Now let's draw it, and then we'll understand it. Take a look at the drawing. I'm going to draw the number 1, and that's what I do. Draw, we say.
Then the character count cuts to 5. 1, 2, 3, 4, 5. It's right there.
And finally,
there's the number 3 as well, since it's also part of the story.
And that must be the number there. It's 3.
So what have we done?
We've set a compass with its center on the number 3.
And then we set the compass radius to 2, took it for a spin around, and found the intersections. Can you see that? That is what we've done geometrically. And it's the geometry that allows us to deeply understand it. If we draw a circle with its center here, and a radius of 2 here, so this distance is 2, then I find one intersection as one solution, and the other intersection as the second solution. And with a radius of 2 here, so this distance is 2, we find this intersection as one solution, and that intersection as the other solution.
Doing okay?
If you've understood that, now listen closely to what I'm about to say next.
What's written here? Can you find all the...
Failure, which is located at a distance of 2 away from the number.
That's what it says here.
I'll say that again.
Can you find me all the x values that are a distance of 2 away from the number 3? Sure, I'll start by marking 3. And then I move 2 to the right, and I get 5. And then I move 2 to the left, and I get 1. They must correspond. Can you see that? And this way of thinking also works with complex numbers. So, if I write it like this, modulus isn't a numeric value, or you could also call it a numeric value. But now we're dealing with complex numbers, so I use the term modulus. Modulus is seed.
-3 should be 2. What does that mean, sir?
That means
we can find all the complex number sets that are at a distance of 2 units from the number. And if I draw it, it won't look exactly like that, but almost. So let's just draw it.
So here is the real axis. Here is the imaginary axis. And first, the marked number is 3. Notice that it's not the number -3 that I should mark. It's the number 3. That's the first thing that can trip you up in your head. Because you see a minus sign, you might think it's -3 we need to look at. It's not. So we heard that the number 3 was important, not -3.
So I head out to the number 3. And of course, it's right where it usually is, here on the real axis.
And then I need to set my compass to a radius of 2. And then I need to place the compass's center right here. So now I've got to draw a circle. And what have I found now? 1, 2, 3, 4, 5. Well, now, I've found 2 real numbers that work, namely the number 1 and the number 5. That's not very surprising, since I got those up there as well. But I found all sorts of others that also work, because it says that you may let each of the complex numbers be set. So what solves this line is the entire circle. All C's on this circle, what can we say about all the complex numbers C on this circle? What can we say about them? They are at a distance of 2 units away.
From the complex number sequence.
Can you see this? So here we have the equation for a circle.
So this is the equation
From a church.
It's an equation for a circle in the complex plane. Goodbye. And connection. And the center in the realm of real numbers. Demo. Now let me take you back in the history book to when you were studying math at B level and remind you of how we described a circle back then. You'll see why complex numbers are essential and elegantly describe circles. Let's try on the next blackboard to rewind back to your B level in math.
Would you like to see if there are any questions about the story here?
All right, let's rewind back to when you first heard about the equation of a circle, and then I'll jump back to this story about numeral signs afterwards and the modulus. Imagine you have a circle with its center at the origin. So here's a coordinate system. Now it's just an x-axis and a y-axis, because now it has nothing to do with complex numbers. So here we have a circle with its center at the origin, and it could be a large circle, just like this one out here. What can I say about every point on the circle? If I pick a random point, then I can probably say something general that applies to all points. So here's a random point that lies on the circle. The point has an x coordinate that I call x and a y coordinate I call y. And there's a distance to the point, which I call r, because that's the radius of the circle. Here you have a small right angled triangle from a 90 degrees angle out to the edge, which, if I enlarge it, looks like this.
X, Y, and 90 degrees.
That means Pythagorean differences, so x brane plus y brane should yield r brane. So x brane plus y brane should equal r brane. If the point with coordinates x lies on the circle, that's why we call it the equation of a circle with the center at the origin and radius r. So we get the equation of a circle, but that requires it to have its center at the origin, 0, 0. And we can read the radius as r.
Let's try looking at a random circle.
This was a lucky circle. It was so lucky. It had a center and radius. But of course, not all circles are that fortunate. So let's try to draw a slightly less lucky circle.
That doesn't have its center in energy curve.
Let's say it has its center right here. And I'm calling the center C for center. The x coordinate of the center I call A, and the y coordinate of the center I call B. And then I draw a circle right here.
And that circle, it has a radius r.
What can I now say about all the points that lie on that circle? Well, I could pick a random point and say something about it, and then I can make sure that it applies to all points on the circle.
And this point right here, I call it P, and it has an X coordinate. I'm calling it X, and it has a Y coordinate. Okay, let's do this.
And now a right angled triangle appears here with a 90-degree angle right here. If I draw it in a larger scale, it looks like this. Here it is. And here's a right angled triangle. Here's the 90 degrees. And how far is it from here to there? So on my drawing, it would be X minus A. So what remains is this part in between.
With
Because
commas.
P is chosen to the right of C. If P was over here, it wouldn't be X minus A. It would be a minus X. Because then A would be the largest.
But what always applies is that it's always the nominal value of x, hey.
Because that way, we're sure that the side length will be positive in that direction, in the triangle.
And how far is it from
And then
here?
the host value must be inverted to the value of Y minus A. And now stores are also in the basement.
Oh no. Yes, my game, of course. Sorry.
And now stores are also included, right? So I can say that this brain plus that brain equals that brain. So I end up with X minus A, the nominal value of it, bracket around that brain, plus bracket the event.
But the numerical value is y minus.
In the second equation, it should yield r squared.
Det der siger I, og det er showing say, den må sige, 3 squared equals 9, and negative 3 times. Negative 3 also equals 9. So it means that this saying becomes irrelevant now, because I'm squaring it. It wasn't irrelevant before, because I had to reverse the saying to get a side length. But now when I raise it to the second power, the sign becomes irrelevant. And that means I can write it like this.
Like x minus a, parentheses, like the formal sign of division.
Fight I minus b squared should equal r squared.
And this too.
It must hold true if point P lays on the circle. That's why it's called the equation of a circle. And which circle does this equation represent? The one with the center. P comes to A.
And the one that has a radius.
So how many circles are there that have a center here and have a certain radius? Just one, and it's that one right there. And this right here is the equation for it. So this is how you were used to describing circles at the B level.
So how do you write it using complex numbers?
Yes, what we saw before, we're now looking back at in complex numbers. Now we're back in complex numbers. If it says something like this.
The modulus of z minus a.
Lim is. So now you have an approximate idea. So all this that is written here, it's written so nicely there now. But what does it mean? The A there, is it the same as that A over there? No, it's not.
But it's there. Is it the same as it being there? Is it?
So if that of isn't the same as that of, then what kind of is it? It's insanely circular, but it's a complex number.
So A is just a complex number that represents the circle's madness.
So A.
It's complex.
And A determines the center. Remember, the complex number represents a point in the plane. So therefore, A can indicate the center.
So if I were to draw this circle using complex numbers, how could I do that?
I can do that over here. Here are the real axis and the imaginary axis. And then I just start by creating a center. Let's call it air.
So this is off. This number is off.
A is a complex number. And then I need to go up to a radio.
It may just be sitting here.
I hope you've taken it to the new loan. So this circle right here is described right here.
Okay, so let's see what it says. Can you clarify what kind of complex number sets lie at a distance?
The Waken, the complex number of.
So it's all the complex numbers that lie on the circle with radius r and center at A.
Okay, place it. So here's a circle with radius r.
And that means once we've invented complex numbers, we can write equations of circles much more simply.
That's the equation for a circle that was
In
invented.
complex numbers,
This right here is the equation of a circle.
after we've developed complex numbers. So for the last part, before I finish talking about this particular topic, let's give an example of how one would describe a set of points. Does anyone have any questions before I do that? Thanks for watching. And once I've done that, you'll get a couple of tasks to try it out for yourselves. Here comes a task I'm making up on the spot. Describe the set of points.
Describe the complex set of points. It sounds really maneuverable. Describe the complex point.
Pump capacity is on, of
Maybe
course.
that's something we can figure
Actually,
out.
it's not hard because here comes the task.
And that's called modulus S.
Set to minus.
2 plus 3i.
It should be equal to 3. This is my task. So now I'll solve it for you and explain my thought process. I can see right away that this looks like the structure I just wrote down, which looked like this.
And what was it that meant? That up there. It meant a circle here.
Which circle is that right there? It's the circle with the center at A, where A is a complex number, so it can be anywhere. And which has a radius R, so it can be as big or as small as necessary. So it's all the circles that can be found drawn at once in the complex plane. But this isn't all circles at once. This is a very specific circle. And what I can immediately say is that its radius must be that one can find inspiration just above the index finger to answer that question.
Danish radio is cool.
Here comes a tricky one. Where is its center?
The inattentive student will say that it must be in point 2,
And that's wrong. It should be 2 minus 3i.
because look up here at the structure. It says Z minus the complex number A. And this can be rewritten like this. And now you see this distance. For A is, of course, a complex number that has 2 components when written in rectangular form. And if I remove the minus parenthesis, it says minus 2, but there's a plus 3. Can you see that? So you have to be careful not to read off the center directly. You need to rewrite it to include a parenthesis first. Otherwise, you won't get the correct center. And of course, this is the classic tricky question you might get in an oral exam. Would you really describe that point? And then the student says that it's a circle with a radius of 3 and a center, 2 plus 3.
And then you say it's not 2 plus 3.
And then they might say 2 minus 3 because they're guessing. And when you ask why, you need to be able to explain that it's because the mathematical structure is called Z minus the center, where the center consists of 2 parts because the center is a complex number. That's why. You just need to rearrange it like this. And then you can clearly see what A is now. You wouldn't see it otherwise unless you give it some extra thought. So now we can see that A is the number 2 minus 3i. By the way, you shouldn't include that minus because it is already in the structure. So that minus sign does not affect what the center is. The center is what comes after the minus. So if the center is what comes after the minus sign, just keep a cool head. The radius must be 3. So now I can draw it. Here comes my drawing of that set of points. So I'll just start by marking the center of this circle. The center was at 2 minus 3i. So I'll move to 2 minus 3i of the real axis.
And then I'm going down 3 on the IMA axis.
And over here in this right here is the corner of rectangles with the center sitting right there. So that's A.
take a note that A is a point on the plan.
It's a complex number, and the radius is supposed to be 3, which means that my circle should come out here, then it needs to hit up there, and then go around like this. So my circle looks continuously circular. So my circle appears to be circularly continuous.
And it has a radius here of 3.
So what does it say here? Describe the complex set of points, blah, blah, blah. What's that? It's all the complex numbers that lie here on this circle, centered on the complex number A, which is 2 minus 3i, and is at a distance of 3 away from that center. So these are all the points on a circle. Can I join in on that example? So what happens if I write like this?
Shut up.
The set of points what if it says the modulus of z minus 2 plus 3i
Less than or equal to 3. What's that now?
What you're hearing read aloud in Danish, that's this.
All the sets of complex numbers are listed here.
Can you describe all the complex numbers C that are at a distance of 3 or less from this complex number A, and now suddenly it's all the points inside the circle. That's called a disk. So this is the set of complex numbers that lie within the circle, and those that lie on the circumference of the circle, that is what we have right here.
So now I can also describe circular disks with complex numbers.
Any questions on that? And notice, of course, the story stops when we get down to a distance of 0. You can't have a distance less than 0. Just like you can't have a negative area, you also can't have a negative distance. That's why it's all the sets lying here, in towards the center, including the center, where the distance is 0, and including all points on the circle, where the distance is 3. All right, now it's your turn. I'm going to make up 2 exercises. Yeah, I'll try to solve them. And we might pause the camera while you work on them. So if you could pause in just a moment. Once I've written down the 2 problems, join in. So it includes all points within the circle, as well as all points that lie on the circle. So it's the circular disk, including the edge. What do you say? Yes. So try to see if you can figure out these 2 tasks here. Describe and draw the set of points the normal value is x minus 1 alone with 3. We're writing the character set. Modulus is set
Plus 2 minus 3i. Into the fray.
What do I set a complete sail at?
So Mina, if you want to pause the recording here, we will try to solve them, and I'll just go around and answer the question. So we've done a bit of practice, and now we've come to the final point for today. It's about the complex exponential function. Let's just review a bit about the real brush we went over once before.
The real exponential function.
So this function is called fx, equals the exponential of x. So imagine you have an input that we call x. So you throw it into this sort of function machine here, and then you use x as the exponent for Euler's number, and out comes a new number, y. The number that comes out depends on the number I put in. So that's what's called the dependent variable, where this number is free to take on all sorts of different values, and that's what we call the independent variable. Then you draw the graph for this function. So we learned at some point that you get an exponentially growing curve. So this here, this is the graph for e to the power of x. And what makes OSCE-XGM such a special mathematical function is that at every point on the graph, no matter where on the graph for non-XGM, the slope of the tangent at that point would be the same as the y value of the point. So if the slope here is 3 on this tangent, then the y value is also 3 at that spot. And it's the only exponential function that at every point has the same slope coefficient for the tangent as its y value at the point. And the domain for this function, the domain of x's is all real numbers. You can see that any x can be used as input. All x's work. The y values that we can get out of the function are limited to only being positive. So that's why we have a range for e to the power of x's.
They are the positive real numbers.
And then there's the feature I just mentioned. If you write it down, if you differentiate with respect to x, e to the x, you end up with e to the x again. This means that e to the x dictates how fast it's growing at each point on its own. You just look at the y value of the point, and it shows you how fast it's growing right there. And that's the only function that does that. So it has some very beautiful properties. The exponential function, which we call the natural one with Euler's number. And that's why we also define it for complex numbers. And that's what we're going to do last for today. We'll talk about the complex exponential function. But let me start with a few remarks about what a complex function actually is, because a real function was something that took x as input and generated y as output. What is a complex function? What is a complex function of a complex variable? Let's start with that. So the heading is now clear. Complex function is a complex variable The matter was indeed simple when it came to real functions. You pick an x from a number line, throw it into the function machine, and then a number comes out on another number line. But this is what the situation looks like here. We begin with a version of the complex plane where we have an x-axis and a y-axis. And here we choose our input. So it could be that I pick an input that lies here called set, and it's within some set over here, which is our domain. So you can see that our domain for a complex function, f, is a region in the plane where the domain for a real function here was either the entire real axis or a subset of the real axis. So now it's either the entire plane or a subset of the plane that is our domain. So you take this C and then you send it off with the function f, and then you land in a new version of the complex plane. Typically the axes are called u and v, and then you land at some point or another. It could be this point here, which is typically called w. So w is a complex number and c is a complex number. And if you throw z into the function, it results in w. And you write it like this. When f acts on the complex number z, you get a new complex number w. So this is a complex function of a complex variable. We take a complex number as input, and we get a complex number as output. And w over here
is located in some region of the UV plane.
And that becomes the range for the function. So we see that both the domain and the range have now become two-dimensional quantities, whereas we're used to them being one-dimensional when we only dealt with real functions. So what happens if you take this function and
define it, f of set, and just like that, with the I counts in the sets?
What do we even mean when we stand like this?
Yes, we believe that when f acts on z, by taking c and using it as the exponent on Euler's number, a new complex number, u, comes out. Ow. Let's see what we get. Let's say that z is written in rectangular form like this, x plus
Thanks
I.
for listening.
It's in rectangular form. What do we get then? If we let f act on that z, alright, so we'll have Euler's number raised to this x plus y. That must be the result that comes out. And this can be rewritten in a clever way because e raised to something plus something else you see in the one times e in the other if we use the power ruling rules. So this can be rewritten as e to the x times e to the x ei. And we can interpret what kind of number that is. This number here is the output w. However, we can say even more than that. By looking here, we can determine two things about w. We can describe the magnitude of w, and we can also describe the argument of w. Because we're used to, when a complex number w is written in this form here, we've almost done that a few times now.
So we're used to this being the modulus.
The thing that comes before beer and
It's
salt.
the modulus of the...
And the number up there, right after the I, that's what we call the argument for w. So if you take a look up there, it's w that we have here. What does it mean then, the real number in front of Euler's number raised to all that's in front?
EJ.
And it's a real number, not just a real number, but a positive real number. So therefore, e to the power of x, that must correspond to the modulus for the complex number. All right, we see that modulus is absolute value.
It won't be extra.
Underline that because it's important. That was actually really important, so let's highlight that.
Modful USB E extra.
And we notice something else. And the argument, that's what comes after the I. And what comes after the I here? That would be y. So we see that the argument comes after the I as well. Good job. This corresponds to my y, and that's important. So we'll put that in a box around it. And now we're ready to calculate an example using the complex exponential function. Let's do an example down here.
We're going out.
Let's say we have a complex number z, which is 2 plus 3i. That's my input, and I want to put that in as the input for the complex exponential function. So I want to figure out what happens when function f acts on the number z. That is, what becomes Euler's number to the power of z. And then we just do what we just did. You'd say that this should yield Euler's number raised to the power of 2 plus 3i. Because that set was just 2 plus 3i. And we break that down into 2. So this must be the same as Euler's number to the power of 2 times Euler's number raised to 3i. So now we can conclude something about this number, which, by the way, is w. That's the output from our function machine.
We can conclude that modulus is w.
So how far away is the output from the origin? That must be Euler's number squared, which answers that. And we can tell what the argument for w is. Three radians. And 1 radian is 57.296 degrees, if I remember correctly. So 180 degrees equals 57.296 degrees. Now you just multiply that by 3. It could be tricky to do that. 3 times 57,296. So we can go ahead and draw the output. So where do we draw the input? We do it right here on the input plane. It's a version of the complex plane. We draw the input over here. Let's see if there are any questions about this before I erase and finish drawing example number 1. It's also pretty cool to get a handle on this story right here, because it's also part of your oral questions, if I remember correctly. So let's try to draw example 1 over here once. And now it should probably be called board number 10.
Sometimes I just forget to add one.
So if I draw this, what would it look like? Well, my input is right here in the first version of the Gauss plan. It's called 2 plus 3 in 1. Okay, let's make it a bit bigger. 1, 2, it's there. And 1, 2, 3, it's there. So my input lies here. That's Z. It's with inputs. Then I'll blast that input off on a space journey with the function called the EZ. Now it's taken off. And now I find Euler's number in the sets.
And
with
practicing
that, I'll
violence
leave the floor
over
open for
here
you to speak.
in Greenland.
Another version of the Gauss plan. Well, the first thing I know is that it lies on a circle with a radius of Euler's number squared. So I can just quickly figure out to the Euler's number R and pi squared.
I obviously can't figure that out because it's 2.5.
7.828828 squared. It's not exactly fun to figure out in your head. So I'll do the math right here. E to the power of pi 1. It comes out to 7.389, but let's just say 7.4 to have a figure, roughly 7.4 here, about 7.4 in physicist notation, 7.4. So I need to draw a circle with a radius of 7.4, which I imagine is right here. So this distance right here is 7.4. That's the radius. And then I need to be rotated up at an angle of 3 radians. I'll also quickly calculate what that is.
So that's 3 times 57, 296.
And that makes 171.9. 171.9 degrees. This is 171.9 degrees.
And that's what I'll draw.
180 degrees is over here. And I need to be about 8 degrees less. So about here. And this is where my output will be at an angle of 3 radians. So that means the point, which was previously called 2 plus 3i, located here, lands here. And what a complex function does is it takes an input from a version of the complex number plane and ends up as an output in a different version of the complex number plane. So typically, you call this the u-axis and the v-axis. Because if you want to write that number in rectangular form, you'd write that w has some u value plus the imaginary unit times some v value.
But we did find w at...
We found w using Euler's formula, e to the power of 2 times e to the 3i. So we can't immediately tell what u and v are without doing some calculations. We'd need to convert to rectangular coordinates. So we figured out where w is located by simply identifying which circle you are on, dear w, and how big an angle you've turned through. That's what we were tasked with immediately when we substituted z into its place in the complex exponential function. Then, getting it in Euler's formula, it would appear right there. Any questions about that explanation? Alternatively, I'll put up a bunch of exercises. You all can enjoy working on them at home. And if you prefer to take a lunch break, you're welcome to go ahead and do that. Otherwise, you can stay seated and do a bit of calculating until the end of the period, which is at 50 past. So basically, you have about 13 minutes left to sit and work on some problems. I'm going to write down a variety of exercises for you, covering everything we've discussed today, including some algebra, a bit of calculus, integrals, and complex numbers. This way, you can get some practice on what we've covered. I'll just move aside so you can take your pictures. I'll just move out of the way so you can take your pictures. And Milan, I might get you to pause while I'm typing because there's a bit of noise when people leave and then it gets picked up in the English translation and stuff like that.
Here's the first part of the tasks. And here are the rest of the assignments for next time.